Hello class. Now I'm going to continue with the second exam, which is type B, Mathematics 2. I'm going to be solving it completely, fully, with details and so on, so that you can understand all the steps, all the processes that went for each solution of each problem. And without further ado, let's begin. Okay, so problem number one, you have an exponential equation to solve. Why is this called an exponential equation? Because the variable appears the exponent. Whether I write this two parentheses or I don't, it makes no difference. There is no ambiguity. Okay, and the same I can do here. I can put parentheses or I can just drop them. Okay, so I give you a hint, a clue. I tell you it's better not to use logarithm base 10 to solve this equation because even though you can use it, it's not a very good idea. Why? Because you can see that these two numbers, guys, 1/3 and 9, these are powers of 3. 1/3 is 3 to the minus 1, so 1/3 is a power of 3, and 9 is also a power of 3. Okay, and when that happens in any particular exponential equation, it's wiser or better. It's better to use the logarithm of that particular base. In this case, it would be much better to use logarithm base 3 to solve this equation. Nevertheless, I'm going to explain to you how you can use logarithm base 10. It's completely irrelevant what logarithm you use. It really makes no difference. I'm just telling you it's a little better to use logarithm base 3. So I'm going to begin with that. I'm going to write using logarithm base 3. So what do? What I do is if I have that this number is equal to all of this number, then it follows that the logarithm base 3 of all of this number must be equal to the logarithm base 3 of all of this number on the right, like so. Then I make use of the properties of logarithms, this one in particular, logarithm base a of x to the n, that's equal to n logarithm base a of x, right? You can drop, you can, yeah, you can lower this exponent and it's gonna stay here. Okay, so I'm gonna do that in here. So basically this exponent and this exponent are gonna be lowered. Like this. Okay, now let's continue. Over here we have the logarithm base 3 of 1/3 and the logarithm base 3 of 1/9. And this is why I told you that it's better to use this particular base, for this particular problem, given the fact that this number and this number are powers of 3, because it's very simple to calculate the logarithm base 3 of 1/3 and the logarithm base 3 of 9. What is this number? This is minus 1, so I can write this. And what is this number? This is 2. Okay, why? Because remember, the logarithm base 3 of 1/3, let me write that in here, logarithm base 3 of 1/3 is that particular number so that when you raise 3 to this number, you get 1/3. And a moment ago, we said that 3 to the minus 1 is 1/3. So that's why this number must be minus 1, because 3 to the minus 1 gives me 1/3. That's why. And now you can see the usefulness of using base 3. Okay, and from here the the solution is pretty straightforward. I'm just gonna do the algebra, just follow it. I don't need to explain anything. So that's the solution. X equals 1, that's it. Now let me tell you, uh, the process is slightly different, slight, slightly different if you use logarithm base t. Only slightly different. And let me do it in here since I don't want to erase this whole thing. Let me do it in here. What if you chose base 10 instead? So we would have something like this: logarithm base 10 of this number on the right. I'm sorry, on the left. This equals logarithm base 10 of the number on the right. There you go. Since you're using logarithms, the same law applies. You can lower the exponent like this. Okay, and at this point is when you can see once again you can see the usefulness of using logarithm base 3 for this particular problem, because in here you cannot calculate easily the logarithm base 10 of 1/3, neither the logarithm base 10 of 9. That doesn't create much of a problem, but I mean that's what I meant by using it, by saying that it's better not to use logarithm base 10, because it's a little harder, just a little harder to solve it in this way, but we still can solve it. What do I do? What I do is this: I'm gonna collect my factors which have the variable on the one side. I'm gonna do this, and I'm gonna collect these constants. You must be aware that this is a constant and this is a constant. Okay, just like 3 or 2 or 1/2, it's just a number that you know. The fact that you don't know the decimal representation of this number makes no difference. Okay, there you go. There you go. And then I'm gonna have to, yes, I will have to erase this. Okay, at this moment you can do this on this right side of the equation. Pay attention. Okay, you're gonna write 9, once again you're gonna write 9 as a power of 3, like that. 9 is 3 to the 2, and 1/3, like we said before, 1/3 is 3 to the minus 1. You see? So I just rewrote all of this into so that it looks now like this. Okay, that's what I did. Why? Because now I can apply once again the rule: logarithm base 10, ignore this, logarithm base 10 of 3 to an exponent. Therefore you can lower the exponent, and it becomes 2 logarithm base 10 of 3 over, lower the exponent, minus 1 logarithm base 10 of 3. And this is where the magic happens. If you can see, since we have two factors multiplying together, on top and two factors multiplying together below, and we have one of the factors being equal to the other, we can cancel them, and thus this become simply 2 over minus 1, which is minus 2. And by the way, I kept the left side unchanged. Clearly, nothing happened on the left side. So basically, I'm saying that x plus 1 over 2x minus 3 is equal to minus 2. And you can see, I mean, right now you can see that it's basically from here. It's a simple problem to solve. Okay, this is just a simple equation, right? You can solve this and you will arrive at the same solution, x equals 1. So that's what you do. That's what you do for this particular equation. Rehearse it. If you got it wrong, if you got it wrong, now, observe the solution, um, and then just do it on your own. 1, 2, 3 times on a row. Understand what I did. Okay, that's the first problem. I'm gonna be taking some pauses in between solutions because this is a very long process, and I may want to go heat my coffee. So let me take just a small pause. Let's continue with number 2. Solve the following logarithmic equation. Leave your answer in exact terms. Do not round or approximate the solution. Remember, guys, what I mean every single time I tell you, leave your answer in exact terms. What that means is this. For example, suppose that after you solve an equation, you get down to this, x equals the square root of 2. Just leave it like that. Leave it like this. There is no um, use, or there is no reason for trying to get this number into some decimal approximation, such as 1.41. No, this is not exact. The square root of 2 is not 1.41. The square root of 2 is a number that is represented by this symbol. That's it. That's all you have to write. Okay? This is the exact term. This is the exact. This is what I mean by saying that leave your answer in exact terms. That's what I mean. So, with that little remark, let's continue. Okay, this is the equation. Let me problem number 2. Let me copy it here. Logarithm base 10, right? Because we don't put the base, so that means that this is base 10. Okay, here is the question. How can I start? Well, I look at this parenthesis, at this trinomial, and I observe that we have a common term, a like term, I'm sorry. So I can just simplify a little bit right from the start. 2x minus x, that's x, minus 1 to the square, minus 2 equals minus 1 plus logarithm of x minus 1. Then, for the same property that I told you on the previous exercise, the previous problem, we can lower this exponent in such way. Okay, then I'm gonna collect or recollect my terms that have a variable, such as this. This term has a variable. We may call it a variable term. This is a constant term, variable term. I'm gonna collect all my variable terms on one side. So I'm gonna leave this one in here, and I'm going to subtract this one from both sides, right? And I'm gonna bring this minus 2 to the other side as adding, like such. And then this plus this, I'm sorry, this minus this, they are like terms. 2 times the logarithm of x minus 1 minus the logarithm of x minus 1, that's simply the logarithm of x minus 1, right? Equals 3. Okay, and we continue over here. So once again, what does this mean? What does this mean? The logarithm base 10 of x minus 1 equals 3. That means that I feel like I did something wrong. Yeah, I got the feeling that I did something wrong. This is wrong. Because I didn't remember seeing a 3 here. Good thing I remembered. Okay, so yeah, it's correct. So what does this mean? It means that 10, which is a base which we don't write, 10 to the 1 is equal to this. That's all it means. Then 10 to the 1 is equal to x minus 1. Well, let me erase the parentheses. Which means that 10 equals x minus 1, which means that x equals 11. And that's it. We're done. Simple problem, simple solution. Let's make a stop and we continue in a moment. Number 3, I give you an equation representing a straight line. How do you know this is a straight line? Because the y variable and the x variable are raised to the first exponent. When that happens, this necessarily represents a straight line. And I give you a series of instructions or a series of questions. So let's do this one. Let me copy the equation. This is problem 3. And the first instruction is this. Rewrite this equation in the form slope-intercept. So here we go. And then we finally multiply by minus 1 on both sides to get this. That's it. That's the solution to letter A. This equation is in slope-intercept. What is the slope? The slope is 1. What is the intercept? Minus 3. B. Rewrite this equation in general form. All I need to do is use these guys and basically just bring everything to the other side. That's it. It's gonna be minus x plus y plus 3 equals 0. That's it. That's all you had to do. Okay. I was telling your other classmates that took the exam type A that there can be many answers for this particular form, for the general form, because if you notice, it's completely valid to multiply an equation, as you may know, by any numbers. For example, what if I multiply this equation by 2 on both sides? What if I do this just because I want to? I mean, it's completely valid, right? If it's valid, I can do it. I'm going to find this minus 2x plus 2y plus 6 equals 0. You see? Look at this other equation. These two equations are the same, guys. When I say that they are the same, I mean it. They are the same. They look different, but they are the same. Why are they the same? Because you can get this out of this, or vice versa. If I take this and I divide it over 2 in both sides, I'm gonna get this one. When you obtain an equation through when you get an equation 2 by means of a valid process from an equation 1, equation 1 gives birth to an equation 2, so to speak. These two equations are the same, mathematically speaking. So you can have many possibilities, let's say, of for this answer, for the general form. They look different, but they are the same. They only look different. Just as this is an example that I tell you very often. This looks different than this, but it's the same number. Okay. And I mean, you may have something different than this and something different than this. It doesn't matter. If I checked it correct, it's because it is correct, and it's because I can get your equation. I'm gonna say this: your equation. I can get it from manipulating this one, but in a valid way. I can arrive to your equation by doing some process like multiplying by 2 or by another constant or something like that, and I can arrive at your specific form of the equation. But it's the same. Both are gonna be the same equations. Find the x-intercept. Find the x-intercept. How do we find the x-intercept of a line? Well, just understand that the line has two intercepts, this one and this one. This is the x-intercept. This is the y-intercept, right? And these 2 points have a feature. Okay, each of these points have a specific feature. For example, this point, if you look at the coordinates of this point, and if you look at the coordinates of this point, there's going to be a 0, either here, 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 or here. For example, for the x-intercept, the coordinate that is 0 is this one, the y-coordinate. All the points in the x-axis, I don't care which one, all these points must have a 0 in the y-coordinate by necessity, right? By necessity. And for the y-intercept, it's the other way around. The coordinate that must be 0 is the x, for obvious reasons too. I mean, you should be able to look to understand this quite clearly. Quite clearly. I'm not exaggerating when I say that. Okay. So if they're asking you for the x-intercept, they're asking you for this point. Okay, and basically they're asking you for this value, this particular value, on the x-axis at which the line crosses such x-axis. So they're asking you for this value, this. How do we find this value? How do I find this value? Well, I know that for this particular point, the y is 0. Okay, so for the x-intercept, y must be 0. Okay, and that's what I need to know. That's what I need to know, because now that I know the equation, for example, I can take this one in the slope form or in the general form, it makes no difference. Then all I need to do is make the y equal 0 right there. Let me do it here. I'm gonna put a 0 in here. That's gonna give me the value of x. X should be 3 according to this equation. And that's it. That's the value of your x-intercept for this particular line. Now you may be thinking, teacher, this is wrong. This drawing is wrong because this point cannot be, I mean, the x-coordinate of this point cannot be positive. I agree with you. I agree, but if you notice, I drew this diagram without telling you that this line was this one. I just drew it in order to illustrate the point. Okay, now in retrospective, now that I know that the x intercept is 3, then yeah, I mean It's 1, 2, 3. The line crosses uh, right here, whether in this way or in this way, I don't know, but it crosses at that point. Okay, so don't be misled by this diagram. So that's the x-intercept. Now the y-intercept, well, just look at this, right? This is the slope-intercept form, and what that means is that you have the slope right here. The slope is 1. We don't put it. We don't write it down, and the intercept is this number. So the intercept is -3. The y-intercept, I mean, is -3. So in fact, this uh, this straight line looks like this: 1, 2, 3, 1, -1, -2, -3. It crosses right here, and it crosses right here. That's it. That's all you need in order to draw properly the graph of this line. Crosses in here and in here. Now this is the diagram for this particular line. And the slope is 1, according to the slope-intercept form of this equation. Problem solved. Listen very carefully to everything I say, like I often tell you, and let's continue with the same problem, with the next problem in a moment. Problem number 4. The following are the equations representing two lines, line 1 and line 2. Here they are. And I ask you two questions. This one has no solution, but this one does. So I made a mistake in here. This is an inconsistent question. Okay, number 4. Let me copy both lines. I'm labeling the lines as line 1 and line 2 for easy reference. Try to adopt that style too. It's very common. Okay, so these are two lines, and I tell you the number k is a constant or a coefficient we don't know so far, and I want you to find the value of k. Find the value of k such that L1 and L2 are perpendicular. So lines, as we know, they can be either perpendicular or parallel or neither. Okay, this is perpendicular, parallel, and this is neither. Okay, and we know what the criteria. We know what the criteria for perpendicularity is. What is the criteria? That the slopes of these two lines, if this is line 1 and this is line 2, the multiplication of the slopes should be -1. So we know the criteria for perpendicularity, and we're gonna use it in a moment. Okay, so if I know that if I want that's the key word. I want line 1 to be perpendicular to line 2. And yes, this is the way you say it. Line 1 is perpendicular to line 2. I want this. Therefore, let me write it down. Therefore, I must have that m1 being the slope of L1 times m2 being the slope of line 2 should be equal to -1. This is what I need. Okay, this is what I need. So first, let's find those two slopes, m1 and m2. How do I find them? I just put my lines into slope-intercept form. That's it. So I take a look at this equation, and I give them this form, the slope-intercept. For example, for the first equation, I'm gonna shape it into slope-intercept form. Here we go. That's it. I'm done. Let me check if I did everything correct. That's it. So this equation is the same as this one, but this is in slope intercept. So right away I can see that m1, the slope of the first line, is -2. Okay, and I just put that in here. I mean, this is not any answer to my problem, right? But I'm gonna make use of this fact. Now I do the same for the other equation. By the way, let me write here line 1 and here line 2. I need to do the same for this other equation. So I'm gonna write it down as it's given. Like this. And then I will do the same. I will shape it. I will shape it into slope intercept. I'm gonna say some steps. I will go directly to the solution. You should be able to arrive at this. It's gonna be kx minus 1. This is it. Okay, just go from here to here. It's just simple algebra. Let me check if everything is right. Yes. Okay. And I realized when I look at this equation, guys, I realized that the slope of the line 2 is k. It's this value. Okay. You may be thinking, well, you may be asking me, teacher, but we don't know what the slope is. I mean, in a way, I understand what you mean. Like, you don't know the value. You don't know if it's a 2 or a 1/2 or a 1/7. I get it, but you know that it's k. That's it. That's it. That's the slope of this line. It's k. It's the number that multiplies the x when you put the equation into slope intercept form. That's it, guys. That's it. Stop thinking of this. Stop thinking of this as not being numbers. These things are numbers. Anything in mathematics, I mean, any variable represents a number. So this is the slope of the second line. And since we said that we must have that the multiplication of the slopes should be equal to -1, let me write that. Let me write the multiplication of m1 and m2 being equal to -1. m1 is -2, m2 is k, that's equal to -1. And therefore, if when I isolate k, I will have that it's -1 over -2, which is 1/2. And that's it. What is my conclusion? My conclusion is this. If I want, that's why I put that in here. If I want this line to be perpendicular to line 2, I must have that the multiplication of the slopes is -1, which is what I wrote in here. And if this is understood as being true, then it follows, se sigue, it follows that k must be 1/2. If k is 1/2, then the multiplication of the slope is -1. And if that happens, then line 1 is perpendicular to line 2. That is the thought process. That is how you arrive at the solution of this problem. Don't worry about B. This is an inconsistent equation. I'm sorry, an inconsistent question. It cannot be solved. Okay, I'm asking for something that it cannot be solved. So I'm just gonna leave it there. Continue with problem number 5. The following are the equations representing two lines. So this is a little similar as the one before, another two equations. And then I ask you to determine whether these lines are parallel, perpendicular, or neither. And I also ask you to find the distance between their y-intercepts. So let's begin. Once again, basically the whole scheme is this, guys. Just put each of these two lines in slope intercept form. Okay, we need to put each of these two lines in slope intercept form. So I'm gonna say that here. Put them in slope intercept form. Why though? Why? Because in such a way I can observe their slopes, right? That's the convenience that this form gives you. It gives you the slope and the intercept of each of these lines immediately. Okay, put them in, and by looking at their slopes, you can know whether they are parallel, perpendicular, or neither. You see, so that's all we have to do. So for the line one, once again, I'm gonna just, I mean, you should be able to do this on your own. I'm just gonna shut up and do it. This last step, going from this line to this line, I divided both sides of the equation by 3. And this is what you get. And finally, it can be written in such a way: minus 2/3 times x plus 3 over 3 is 1. So this is line 1 in slope intercept form. And I will do the same for the line number 2. Like this, I think I'm correct. Am I missing something? No. 2x plus 4. Yeah, everything seems to be okay. This is x. Yeah, it's okay. I hope I'm not missing something. If you see any mistake, please tell me immediately. So this is line 1 and this is line 2. Line 1, line 2 in slope intercept. Therefore, I can observe their slopes. The slope 1 is minus 2/3. The slope 2 is 2. And I mean, it's clear that they're not the same. Okay, so since these are not the same, conclusion, they're not parallel. Okay, because for parallel lines, you must have both slopes to be, they have to be the same. Now, their multiplication is also not equal to minus 1. When you multiply 2 times minus 2/3, this is not going to be equal to minus 1. Conclusion, these are not perpendicular. So what is the other only conclusion? If not parallel, if not perpendicular, then neither. Okay? Conclusion, neither parallel nor perpendicular. That's it. That's my conclusion. And the other question is quite easy, straightforward. Find the distance between the y-intercepts. Look at the y-intercepts. It's 1 and minus 4. Okay, what that means is if you gotta look at a Cartesian plane in which both lines L1 and L2 are drawn, then you'd realize that the line 1 crosses the y-axis at this value, at 1, and the line 2 crosses the y-axis. In other words, its y-intercept is minus 4. So it's about here, more or less. See, this is the y-intercept of this line. This is the y-intercept of this line. What is the distance between the y-intercepts? It's 5. 1, 2, 3, 4, 5. As we can see, from 1 to minus 4, you have 5 units, and that's the distance. 5 units. That solves the problem. Let's make a pause, and I'll get back at you. Problem number 6. Given this function, find several things. Okay. So this is a simple. This is a very simple problem. This is a function. Problem number 6. Of x equals 2x to the cube minus 5, and the question A is find f of minus 1. Remember, what this means is evaluate. I mean, there are several ways by which you can understand this symbol. This can be said to be an evaluation of f in this value of the input. Okay, or you can also read sometimes calculate f of minus 1, and other maybe another couple of ways you can say this: f of minus 1, the value of f in x equals minus 1, etc. So what is this? It's just a simple substitution. If you know that f of x is equal to 2x to the cube minus 5, then f of minus 1 is 2 times minus 1 to the cube minus 5. This is it, guys. As long as you did this, you should have this question correctly checked. If you did this only, okay, if you continued with the process, that's also okay. But as long as you did this, you should have it correctly. B, find the value of the function in 3 halves. So that's going to be equal to this. And once again, as long as you wrote this, that's correct. And if you continued with the whole process, that's also right. What's this? That's going to be 18 over 4 minus 20 over 4, which is minus 2/4, which is minus 1/2. If I'm correct, yes, it's minus 1/2. C, find the value of the function in 1 minus a squared. Okay, it's the same idea. Same idea. The fact that, please do not read this as something weird. This is just a number, just as 3 halves or minus 1. There's nothing weird about this, guys. Nothing weird. The same stuff that you did on the previous two, that's the same stuff that you're going to do for this one. All you have to do is this. This will be equal to 2 times this value to the cube minus 5. That's it. Period. Done. You don't have to continue with the whole thing like raising this to the cube and blah blah blah. That's, I mean, it's not necessary. You could have, and by the way, some of you did this wrong. For those of you who did this wrong, please check once again your most basic algebra, because by now, I mean, I cannot accept that you don't know how to raise a binomial to the cube. It's such a simple thing. Such a simple thing. I mean, just go down to the basics and multiply that stuff 3 times like this. 1 minus a squared times itself 3 times. That's what it means. That's it. Some people got this wrong. That's pretty serious, guys. Okay, ABC down. What about D? Find the value or the values of x for which we get f of x equals minus 38 over 8. So this is kind of like the reverse process. Once again, your function is this. And now I'm asking you not to evaluate the function in a specific value of x, but kind of the reverse process. I'm giving you already the output. You see? I'm giving you for some x, f of x is equal to minus 38 over 8. For some x, f of x equals minus 38 over 8. Basically, I'm asking you find x. That's it. So basically just replace in here this value. That's all you had to do, guys, like this. And then obviously find x, because I'm asking you to find x. It's not enough to do this. So just continue. Minus 38 over 8 plus 5 equals 2x to the cube. This is minus 38 over 8 plus 40 over 8 equals 2x to the cube. This is 2h equals 2x to the cube. We divide over 2 and we get 2 16ths equals x to the cube. I'm going to continue over here. X to the cube equals 1 over 8, which is the same as this, right? And finally, x equals the cubic root of 1/8, which is the same as 1/2. That's it. But by the way, if you arrived at either at this point, that is good enough. Like there is no need to go to the most simplified version of the cubic root of 1/8. This is good enough. This is a little better. E, find the value or values of x for which we get f of x equals 0. So, same idea. It's pretty much the same as before. This is another value. Instead of this one, now 0. But it's the same idea. We have this. Let me flip the sides. Let me continue over here. And let me take this the cubic root. And I'm done. That's it. F. Which of the following sets of ordered pairs might represent the function f? Neither. Neither, because when you try each of these ordered pairs, like for example, let's take a look at this one as the first at the first set. We have 3 points, and each correspond to a pair of input output, right? Input output, input output, input output. One of these is gonna fail to correspond to this function, right? For example, the first one, 1 comma minus 3, we should have that f of 1 should be equal to minus 3. We should have this according to this function. Is that true though? Let's see, f of 1 is 2 times 1 to the cube minus 5. F of 1 is 2 minus 5, which is minus 3. Okay, this one checks. This one checks. So far, so good. At some point, one of these two will break. Is it going to be this one? It's this one. This one, this one, this specific point does not satisfy this function. Okay, or in how can I say this in another way? If you put this input of 2 into this function, you won't get 4. If you want me to completely convince you of this, let's just do the math. F of 2 is equal to this, right? So this is 2 times 8 minus 5. This is 16 minus 5. And this is 9. So this is the output for this particular input. Input of 2, output of 9 for this function. And this set has the following. For an input of 2, it gives you an output of 4. Therefore, this particular point doesn't belong to f. Therefore, this set cannot represent the function f. And the same is going to happen for the other one. So the answer is neither. And which of the following graphs represents the function f? It's this one, the first one. How do you know? Let me enlarge this thing. How do you know that this function is the one? I'm sorry, how do you know that this graph is the one that corresponds to this particular function? Okay, same idea. All that you have to understand that a graph is the collection of points, the collection of ordered pairs that make f. For example, look at this point. Look at this point. This point is, that point is 0 comma minus 5. Okay. What other point? Well, I guess this is enough. There's let's look at this one right here. This is a very clear point. What point is this? It's minus 1 minus 7. Okay, so with these 2 points you can actually tell, with these 2 points, if these 2 points satisfy the function f, okay, that gives you a, I mean, it's not enough, but it gives you a good idea that this is the graph that corresponds to f. Okay, maybe I should clarify this a little better in class. Like, how do you know if I give you a graph and I give you a function like f of x equals something, how do you know that such graph corresponds to such function? Maybe I should clarify that stuff. Okay, so that ends problem number 6. Now we continue with problem number 7. Find the domain of the following functions. Okay, so what is the domain? Remember, guys, the domain of a function is all the possible values for the input that we can give to such function. I mean, mostly when they are represented as equations. When they are when you have a function given as an equation, then as the domain of such function, you have to consider all the possible values for the input that don't cause problems. Remember, quotation mark. What do I mean by problems? Divisions over 0, or the calculation of roots, even roots of negative numbers. What I mean by even, I mean that they can be the square root, or the fourth root, or the sixth root, etc. of a negative number. That's just impossible at the moment. So let's observe these functions. This function has as domain all the real numbers because we never run the risk of dividing over 0 or having the calculation of an even root of a negative number, right? Because of the way the function is given. You see, we never run neither this nor this problem. We never done the risk of encountering these problems. The next function, g of x, we have an even root of 2 minus x, so we should be careful and we should analyze. So we have the square root of 2 minus x, right? And how can you do this? Like, how can you find what's going to be all the possible sets of, what is the set of all the possible inputs? Well, imagine your x-axis, which is the axis for the inputs, right? Imagine the 0, the 1, the 2, the -1, the -2, etc. And just do experiments if that's the way you want to approach this. Like give x the value of 1, everything is gonna be fine. Give x the value of 2, everything is gonna be fine, because you will be calculating this, right? The square root of 2 minus 2, which is the square root of 0, and that's perfectly possible, which is 0. The moment you give any value beyond 2, for example 3, 2 minus 3 minus 1, you're gonna be calculating the square root of -1. It's impossible. For 3 onwards, uh, this is not accepted. But not just from 3 onwards, but any number in here, guys, any number starting from 2 onwards, like all of these values, all of these, all of these, slightly larger than 2, anything above 2 will crash this function. Anything above 2, and anything below 2 and including 2, we should be very specific, anything below 2 and including 2 will be perfect. Everything in this blue segment is perfect. Any number in here and any number in the red segment will crash this function, so that I have enough information to write my domain. The domain will be then the following. The domain of G is all the numbers from -infinity up until 2, including, like this. Or I can also write all real numbers below 2 and including 2. See, I often tell you that there are many ways you can specify a domain, and each of these ways is perfect. H of x, we have the following: 2 over 5 minus x over 2. Do we run the risk of encountering a problem? Yes, because in this denominator we have a variable, and depending on what this variable is, we may have this denominator being equal to 0. So let's just ask the question: do we have that this is equal to 0 for some x? Is it possible? The answer is yes. Why? Because if we try to solve this equation, we're gonna get this 5 equals x over 2, and then 10 equals x. So for this value of x being 10, the denominator will be 0, and that's going to cause a problem. This value will cause a problem in this function. And that's the only value that will cause a problem. So what is my conclusion? My conclusion is that the domain for the function h is all the real numbers except the number 10. Okay, and if you write down with words everything I said, all the real numbers except the number 10. That's also perfect. And if you want to write this, that's also perfect, because you're telling me with this that you're considering all the numbers from minus infinity to 10, excluding 10, excluding 10, and then unite this bit with this other bit, which is starting from 10 but excluding 10 on onto infinity. So if we want to represent this visually, we have something like this. This is 0. Let's imagine the number 10 is here, and it's gonna look like this more or less. All these numbers are including, excluding 10, excluding 10. This accounts for this bit, and then unite this bit or this segment with this other bit, which is right from 10 but excluding 10 also onto infinity. So when you see these guys, basically all of this means all the numbers except this very particular one. That's the only number that we are excluding by this symbology, which is the same as this, which is the same as this. This one now, I of x equals x over x squared minus 4x minus 21. Once again, we have a variable in the denominator and we run the risk of dividing over 0 because of that. This variable in the numerator doesn't carry any significance in this regard. Like this will not cause any problem. Only the ones that appear in the denominator can cause problems. So let me ask the question again. Is this trinomial equal to 0 for some x? How do I answer that question? I solve this equation, or I try to solve it. Maybe it has no solutions. If it has solutions, then this question is solved in the affirmative or in the positive. If this has no solutions, then this question has an answer in the negative. Okay, so let's try to solve it. By factorization, you will see that this trinomial is equal to this factorization. If I'm correct, yes. And basically the solutions are 7 or also minus 3. That's it. So I could find solutions for this equation, and what that tells me is that yes. Is this equal to 0 for some x? The answer is yes, because I actually found those values. And that's it. That's it. What is my conclusion for this particular function? The domain of I is all the real numbers except the number 7 and the number minus 3. And this one, very quickly here, we have this. J of x equals x over x squared minus 1. Once again, is this possibly equal to 0? Let me erase the whole thing. Can this denominator be equal to 0? Yes. It's pretty obvious, right? Try to solve the equation, and you will see that the solutions in plural, the solutions will be plus 1 and minus 1. If you input in that x either the plus 1 or the minus 1, all of these will become 0, and therefore these values should be excluded from the domain of this function. My conclusion is that the domain of J is all the real numbers except 1 and minus 1. And that solves this problem. And let's finish with the last one already. So we have this, the weight that a person gains per day, established by a W and given in grams, and the number of calories consumed per day, C, are related through the equation, this one. Does this, question A, does this relation represent a function? Argue your answer. The answer is yes. The reason, because for each amount of calories, you can have one and only one and only one. This is the key phrase. One and only one respective weight gain for each amount of calories consumed daily. Okay, so if this is the set of the inputs, this is the set of the outputs, this is the amount of calories consumed per day, this is the weight gain per day, and when you consume a certain amount of calories, you will be gaining a certain amount of weight. And only one and only one. You never have two possibilities. For the same amount of calories, you never have two possibilities for the weight gain. And that's what makes this a function. That's it. It's that simple. Express this relation through functional notation. Well, you can do this. F of double, I'm sorry, F of C equals 0.1 C minus 2000. Okay, this is the output, and this is my input. This is my input variable, the amount of calories, and all of this symbol is my output variable, which is the same as the weight. Okay, and the relationship between the weight gain and the calories is given by this, right? That this allows you to calculate the weight gain if you know the number of calories ingested. Done and done. Calculate the number of grams of weight gain if the person consumes 4,000 calories on a given day. Use functional notation for this. Well, once that I know that this is my function, then I just, I'm sorry, for letter C, I'm just evaluating F in 400 calories. So basically, you just had to do this. 4,000 minus 2,000. That's it. This is 2,000 times 0.1. That's 200. So F of 4,000 equals 200. What is the interpretation of this? How do I interpret this equation or this result? What this means is the following. When a person consumes 4,000 calories, the weight gain is 200 grams. That's it, period. And D, on a given day, you realize that a person gains 500, I'm sorry, 150 grams of weight. How many calories did she consume? So this is the reverse problem, in which you know the output, okay? You know the amount of weight gained, which is 150, and you want to know how many calories this person consumed. So basically, we want to solve this equation. 150 equals 0.1 times this. In other words, we have this. In other words, we have this. 150 plus 200, 350 equals 0.1 C, and then we just divide 350 over 0.1, that's C, and therefore C equals 3,500 calories. That's it. And this concludes the process of the solution, guys. I hope you have learned something in case you checked it. Thank you very much.